Hello and welcome to my YouTube channel Petro Intelligence. My name is Shahid Khan, and I am a chemical engineer. Today we will discuss refrigeration systems and introduction to centrifugal compressors. Waste heat must occasionally be removed from a process at below ambient temperatures. This is normally accomplished by evaporating a light fluid called a refrigerant. Common industrial refrigerants are ammonia, propane, freon. Your home central air conditioning system is a good example of a simple refrigeration loop shown in picture illustrates the basic components. Refrigerant motor-driven compressor. Refrigerant condenser. Refrigerant letdown valve. Evaporator. Refrigerant receiver. The basic process flow of the refrigerant system is 1. The compressed refrigerant vapor is discharged from the compressor. This vapor is superheated, meaning that it is above its dew point temperature. 2. The vapor is next cooled and condensed in the refrigerant condenser. Typically, 75 to 80% of the condenser heat duty is the latent heat of condensation of the refrigerant. The remaining heat duty is sensible heat removal. The sensible heat removed is a combination of desuperheating the vapor and subcooling the condensed liquid refrigerant. 3. The subcooled refrigerant next flows into the refrigerant receiver. Subcooled means that the refrigerant temperature is below its boiling point or bubble point temperature. The liquid refrigerant loses a small amount of pressure as it enters the receiver. The pressure loss is due to friction in the piping and an increase in the elevation of the refrigerant as it enters the receiver. 4. The condensed liquid refrigerant next flows through the letdown valve. In picture, this letdown valve is not controlling the receiver liquid level. The receiver level is allowed to vary as the total refrigerant inventory changes. This idea can be better understood if we remember that this is a closed system. That is, we have to take swings in the refrigerant inventory somewhere in the system. 5. The refrigerant liquid partially flashes to a vapor as it flows through the letdown valve. The flashing represents the conversion of the sensible heat of the refrigerant to latent heat of vaporization. In picture, the refrigerant is chilled from 100 to 40 degrees Fahrenheit. Approximately 25% of the liquid flashes to a vapor to provide this auto-refrigeration. The compressor, motor, condenser, receiver, and letdown valve are all components of your home central air conditioning unit. They are installed as a package, surrounded by the condenser, outside your house. The evaporator is located in your attic. To continue our description of the process flow. 6. The partially vaporized refrigerant flows into the evaporator. In picture, the evaporator shown is similar to a kettle-type reboiler. The process fluid flows through the tube side of the kettle evaporator. The refrigerant liquid level is maintained by the letdown valve. The refrigerant vapor flows from the top of the kettle to the compressor suction. 7. The motor-driven compressor boosts the pressure of the refrigerant vapors from the evaporator pressure up to the condenser pressure. Refrigerant receiver. Looking at picture, the need for the refrigerant receiver is not immediately obvious. It does not appear to serve any process function. Many refrigerant systems are constructed without this vessel. However, it does have several important uses. For one thing, it provides a quiet zone for entrained lubricating and seal oils to settle out. Lubricating and seal oil often leak into the circulating refrigerant. The lower the suction pressure of the compressor, the greater the problem. Eventually, the amount of heavy oil that accumulates in the evaporator will cause a problem. The heavy oil is largely insoluble in the refrigerant. As the refrigerant boils away out of the evaporator, the heavy oil is left behind. This oil partly coats the refrigerant tubes. The heat transfer efficiency of the evaporator is reduced. Turbulence caused by the boiling of the refrigerant prevents efficient draining of heavy oil from the evaporator. However, if the refrigerant receiver has been designed properly, it can be used to trap out the heavy lubricating oil. Inventory control. In picture, there are two levels that must be controlled, the evaporator level and the refrigerant receiver level. It is impossible to control both levels with two-level control valves. One level must be held with a level control valve. The other level must be held by adjusting the system liquid refrigerant inventory. It is usually better to add makeup refrigerant to keep a decent liquid level in the receiver and control the flow of refrigerant into the evaporator. However, reversing this control scheme by adjusting inventory control in the evaporator is also possible. Vapor trap. Another way of looking at the receiver vessel is to think of it as a giant steam trap. As long as the liquid level is maintained in the receiver, uncondensed refrigerant vapors cannot escape from the condenser. Let's assume that such vapors did escape from the condenser. If there were no refrigerant receiver vessel, these vapors would blow through the letdown valve. Reducing the pressure of the vapors produces just a tiny bit of refrigeration as compared to vaporization of liquefied refrigerant. Now let's assume that there is a refrigerant receiver between the condenser and letdown valve. This traps any uncondensed vapors. The accumulation of these vapors raises the pressure in the receiver. This puts back pressure on the condenser. The higher condenser pressure promotes more complete condensation of the refrigerant vapors. Finally, the receiver will accumulate any non-condensable, or hard-to-condense, components that have accidentally entered the system. Air left in the vessels on startup is one such example. Traces of methane and ethane in a propane refrigerant system are another. These light vapors may be vented from the top of the receiver during normal operations. Evaporator temperature control. The system shown in picture has no provision for controlling the evaporator temperature. This is controlled solely by the compressor suction pressure. The lower the compressor suction pressure, the lower the evaporator temperature. This is exactly how our home air conditioner works. If the evaporator temperature is too cold, what can we do? Well, if this were a steam turbine compressor, gas engine drive, or any other type of variable speed driver, we could reduce the compressor's speed. This would reduce the flow of refrigerant and raise both the evaporator and compressor suction pressure. But we are working with an ordinary AC, alternating current, motor, which is a fixed speed device. There are then three methods available to control the temperature in the evaporator: spillback, discharge throttling, and suction throttling. Spillback. Spillback bypasses the compressor discharge gas back to the compressor suction. This is a relatively energy-inefficient way to increase the evaporator temperature. Spillback is discussed in other lecture on centrifugal compressors and surge. Discharge throttling. Discharge throttling is also an energy-inefficient way to control the evaporator temperature. Even worse, if we are working with a centrifugal compressor, discharge throttling may cause the compressor to surge. Suction throttling. Suction throttling is the preferred method, as shown in picture. Suction throttling also wastes energy. Whenever a control valve is partially closed in any service, energy is always wasted. But with a fixed-speed centrifugal compressor, it is still the best option. As the suction valve is closed, two things happen. The flow of refrigerant vapor to the compressor is reduced, and the compressor's suction pressure drops. The reduction in the refrigerant vapor flow reduces the workload on the compressor. But the reduction in the suction pressure increases the compression ratio, discharge pressure divided by suction pressure. This increases the workload on the compressor. As we have discussed in our lecture on centrifugal compressors and surge, increasing the compression ratio is a small effect on compressor workload as compared to decreasing the vapor flow, as long as we are operating on the flat part of the compressor's flow versus the head performance curve, which is almost always the case for a centrifugal machine. Hence, suction throttling will significantly reduce the horsepower load on the compressor, as well as increase the evaporator temperature for a motor-driven compressor. Suction throttling is usually done with a butterfly control valve, which has a very low pressure drop when it is wide open. Compressor operation. Let's say we have a centrifugal refrigeration compressor driven by a motor. The motor is tripping off because of high amperage. Should we open or close the suction throttle valve shown in picture? Answer is close it. Of course, both the evaporator vapor outlet temperature and the process fluid outlet temperature will increase. But that is the price we pay for having too small a motor driver on the compressor. Does this mean that when our home air conditioner gets low on Freon, our electric bill drops? Correct. But the price we pay is a hot home. How about the compressor discharge pressure? What is this controlled by? Answer is the condenser. The compressor discharge pressure has nothing whatsoever to do with the compressor. And this statement is true regardless of whether the compressor is a reciprocating or centrifugal machine, or fixed or variable speed. It is the condenser temperature that determines the compressor discharge pressure. Lowering the compressor discharge pressure can be achieved by providing cooler water to the refrigerant condenser. But how does this affect the horsepower load or electrical power demand on the compressor's driver? It depends on how much the refrigerant vapor flow increases, as the compressor discharge pressure is reduced. For instance, suppose we are working with a reciprocating compressor. This particular machine has a very small volumetric clearance and a very high volumetric efficiency. These terms are explained in my lecture on reciprocating compressors. With this compressor, a significant decrease in discharge pressure will result in only a tiny increase in vapor flow. Therefore, the work or amp load on the driver will decrease. On the other hand, suppose we are working with a centrifugal compressor. This particular machine has a flat operating curve. This means that a small decrease in discharge pressure will result in a large increase in vapor flow. Therefore, the load on this compressor's driver will increase. This discussion assumes that the compressor's suction pressure is fixed. However, in the real world, this is rarely the case. As we lower the compressor discharge pressure, the compressor suction pressure will also decrease. This will have the normally beneficial effect of reducing the evaporator pressure and temperature. Now that the evaporator is cooler, we could increase the flow of warm process fluid to the evaporator. Thus, improving the efficiency of the condenser will increase the capacity of a refrigeration system to cool. This happens mainly by lowering the compressor discharge pressure rather than producing a colder condensed refrigerant. Condenser operation. A closed-loop refrigerant condenser ought to be one of the cleanest services in a process plant. Even seal or lube oil leaks affect the evaporator efficiency rather than the condenser. I have measured rather high, for example, 140 BTU per hour square feet degree F heat transfer coefficients in such condensers, even after that condenser has been in service for several years since its last cleaning. The most common problem with refrigeration condensers is condensate backup, rather than fouling. This may happen if the condenser outlet line is undersized. Let's say that the pressure drop due to piping friction losses in this line is 10 psi. The refrigerant is isobutane. The isobutane cannot flash as it enters the refrigerant receiver. The reason it cannot partially vaporize is that there is no vapor outlet from the receiver. If it were to vaporize, it would slightly increase the receiver pressure. This would push up the liquid level in the condenser. Many of the tubes in the condenser would be submerged in the liquid refrigerant. The refrigerant would be subcooled below its condensation or bubble point temperature. It would have to be subcooled, so that after the liquid lost 10 psi of pressure it would not flash. To subcool isobutane so as to prevent it from vaporizing after losing 10 psi, the isobutane vapor pressure must be reduced by 10 psi. This would, in turn, require cooling the isobutane by about 5 degrees Fahrenheit shown in picture. Unfortunately, subcooling a liquid is difficult. This means that the heat transfer coefficient for subcooling might be 30 BTU per hour square feet degree F. Even though the amount of heat to be removed in subcooling a refrigerant is small, it may require 30% of the tubes in the condenser to do the job. The reason is the low heat transfer coefficient for subcooling as compared to the high heat transfer coefficient for condensation. The tubes in the condenser required for subcooling reduce the heat transfer surface area required for condensation. In effect, the condenser shrinks. This makes it more difficult to liquefy the refrigerant vapor. The vapor is then forced to condense at a higher temperature and pressure. Of course, this raises the compressor discharge pressure. And, as we have discussed in the lecture, this increase in compressor discharge pressure invariably reduces the compressor's capacity and may also increase the horsepower needed to drive the compressor. An increase in the elevation of the receiver will reduce the pressure of the liquid refrigerant. This loss in pressure due to increased elevation will also require an increase in the surface area of the condenser devoted to subcooling. Refrigerant composition. A very large percentage of refrigeration systems are not limited by the compressor driver horsepower, the condenser, or the evaporator. Many refrigeration systems are limited by either compressor suction volume limits, the mechanical pressure rating of the compressor case, or the refrigerant condenser shell. If the compressor is suction volume limited, we say that it is speed limited. If the compressor is driven by an AC motor, its speed is determined by the motor speed and any connecting gears. If the compressor is driven by a turbine, then the rated speed of the turbine limits the compressor speed. Overcoming speed limits. While the actual cubic feet of refrigerant vapor to the compressor may be limited by the compressor's speed, we can still overcome this bottleneck. The trick is to make the refrigerant lighter or more volatile. A lighter refrigerant will allow the evaporator, shown in picture, to operate at a higher pressure or a lower temperature. Increasing the suction pressure increases the density of the refrigerant vapor flowing to the compressor. Even though the volume of gas flow is constant, the weight flow of the circulating refrigerant can be increased. Yes, we can get 6 pounds of manure in a 5-pound bag if we make the manure denser. For example, adding lighter propane to heavier isobutane in a refinery alkylation unit is a common practice to increase refrigerant circulation. But this will work only when the compressor's driver has spare capacity. Of course, in process operations, there are no free lunches. Spiking propane into isobutane also makes the lighter refrigerant more difficult to condense. This will raise the compressor discharge pressure. Also, the operating pressure on the shell side of the condenser will increase. If either piece of equipment does not have an adequate design pressure, then increasing the volatility of the refrigerant cannot be permitted. An engineer used this trick at the refinery to increase the refrigeration capacity of sulfuric acid alkylation unit. He found that capacity was limited to 18,000 BSD by the refrigerant circulation rate. He had plenty of compressor capacity, but as he increased the turbine speed to run his compressor faster and circulate more isobutane refrigerant, the compressor's suction pressure declined to 1 psig. Running the compressor suction below atmospheric pressure is possible, but dangerous. Oxygen can be drawn into the refrigerant loop due to minor air leaks in the suction piping. To avoid this potential hazard, one should always maintain a positive pressure at the suction of any refrigeration compressor. To overcome this limitation, he increased the propane content of his circulating isobutane refrigerant from 5 to 10%. This required several hours. As the suction pressure rose due to the more volatile refrigerant, the operators increased the refrigerant compressor speed, and hence the refrigerant circulation rate. Eventually, using this and other tricks, he increased unit capacity to 25,000 BSD. Pressure rating limits. The simplest way to lower the compressor discharge pressure is to reduce the cooling water temperature to the condenser. One trick is to use the cooling tower makeup water on a once-through basis to the refrigerant condensers. This supply of water is almost always 10 to 20 degrees Fahrenheit cooler than the cooling water supply. Another way to reduce the compressor discharge pressure is to make the refrigerant heavier or less volatile. Adding isobutane to a propane refrigerant is one example. This will lower the suction pressure to the refrigerant compressor shown in picture and increase the actual volume of vapor flow. If the compressor is speed limited, this will not be practical. Adjusting the refrigerant composition does not significantly affect the amount of horsepower needed to provide a fixed amount of cooling at a certain evaporator temperature. This statement is true even if the type of refrigerant used is changed completely. Propane, isobutane, freon, and ammonia all have roughly the same refrigeration efficiency. That's all, gentlemen. If you like my video, please follow my YouTube channel Petro Intelligence for more videos.